So in the last class, Hamza, are you getting my voice? Hello, Hamza. Hello.
Assalamu alaikum.
Walaikum assalam. So in the last class, I have discussed the motional EMF. Motional EMF means when the wire will move in the magnetic field with some speed or velocity, then there will be the EMF and in the wire, and that EMF is known as the motional EMF. Now this we will discuss how to decide the polarity of induced EMF in a conductor. So suppose here is a wire in the given magnetic field. Suppose this is the wire or this is the conductor we have. This is one end of the conductor. This is another end of the conductor. AV is the wire of length L. And this wire or the conductor is moving with some velocity in this direction. And this is this represents the outwards inwards magnetic field. Okay. So magnetic field is inwards. So we have to decide that which end of the conductor will be positive and which end of the conductor will be negative. Okay. Why there will be the EMF? Because this conductor is moving in the magnetic field. There will be the change in the magnetic flux with respect to this wire. We have already discussed. Okay. This case. Here, this conductor is moving in the magnetic field inwards, and here is the EMF induced in this wire. So we have to decide that which end of the wire is positive, which end of the wire is negative. So first of all, we should know the direction of the force on this wire, direction of the magnetic force on this wire. FB is the magnetic force. So what will happen? There will be some induced current in this wire, and this will be the case when you can say that the wire carrying a current present in the magnetic field. So this wire will experience a force, and direction of that force. So Nida, I have started this topic last class. Till here I have completed. So I have started from here. How to decide the polarity of induced EMF in a conductor. So in a given magnetic field that is inward, a conductor is there, and this conductor is moving in this direction with some velocity. So in this conductor, there will be the induced EMF. Okay, there will be the induced EMF, and what will happen? This conductor will experience a magnetic force. This conductor or this wire will experience a magnetic force, and the magnetic force on a wire is given by magnetic force on a given in a wire is given by I into L cross V. This is the case, and for finding the polarity of the ends of the conductor, suppose there is one E positive charge, here inside the conductor. So instead of this, I will use this formula. Magnetic force on this E positive charge is given by the value of the charge into the velocity into magnetic field. Okay, as this wire is moving in this direction, so this charge will also move in this direction. So for finding the direction, first you should know the velocity of this wire is along x-axis, and the magnetic field is in the y-axis. Okay, so the magnetic not in the y-axis, magnetic field is along the negative z-axis, that is inward. So magnetic force should be in the y-axis. Okay, along the y-axis, because this magnetic force is a cross product of the velocity and the magnetic field. Okay, so you can write the magnetic force not on the wire, magnetic force on this E positive charge. Magnetic force on the E positive charge is perpendicular to the velocity of the wire, and magnetic force is also perpendicular to the magnetic field. So for this, point your fingers along the direction of the velocity and curl towards the magnetic field. So point your fingers towards the velocity and curl toward the magnetic field. Magnetic field is inwards. Magnetic field is inwards. Inwards means away from you into the screen. So inwards, so you will get the direction of the force on this E positive charge in the upward direction. Means this E positive charge is going in this direction. Okay. E positive charge is going in this direction. So as this positive charge is going in this direction, so you can say this end of the conductor will be positive and this end of the conductor will be negative. Okay. But what is happening? This you have taken for this with respect to this positive charge, but in actual, in the wire we have the electrons. If force on the positive charge in the upward direction, then force on the electron will be in this direction. Okay, force on the electron will be in this direction. So electron is moving from negative to positive, so the direction of the polarity or the polarity of this conductor will be negative to positive. This end will be the negative and this end will be the positive. Okay, so now I will discuss the what is angular velocity. Angular velocity. So angular velocity means suppose here is a particle Here is a particle, and that particle is moving on this circle. A particle is moving on this circle. Okay, and this circle have the radius capital R. So angular velocity is represented by omega. Angular velocity is represented by omega, and here v is the linear velocity, or the velocity, simply you can say. This is the velocity of the particle, and if this particle is suppose here at this point, so if a particle is moving along the circular path, then always the velocity of the particle will be tangential. So if the particle is at this point, then here also the velocity of the particle will be along the tangent. Direction of the velocity will be along the tangent to this point. If suppose your particle is here, then you want to find the direction of the velocity here at this point, then you will draw a tangent like this. You will get the direction of the velocity. Suppose this particle is initially at this point and finally at this point. This is the initial condition and this is the final condition. And angle subtended by this initial and the final position is theta. Okay, the angle subtended by this, the particle has moved from this point to this point, initial to final. So this particle subtended means swept an angle of theta. So what is omega? Omega is equal to the angle swept in a given time. Okay, angle swept by the particle means in moving from this initial to the final position, the angle theta divided by the time taken in moving from initial to the final position is known as the angular velocity, that is omega. Okay, and what is theta? Theta is known as the angular displacement. Angular displacement. Okay. Or this omega can be written as, if you want to find the instantaneous omega, means at an instant of time, then this omega is given by the differential form d theta by dt. Okay, d theta by dt. This is the instantaneous angular velocity. Okay, write down this. Just a minute. Actually, we have done a mistake here. Here, what you will do? Here you will assume the electron of this wire, and the force on the electron of this wire is in this direction. When you will apply the right hand rule, point your finger in the direction of the velocity and curve towards the magnetic field, you will get the magnetic force on the electron. So this means that the electron is moving in this direction. Okay, so this end will be negative, not positive. Just a minute. This end will be, electron is moving in this direction, and electron moves from the negative terminal to the positive terminal. So this will be the negative terminal, this will be the positive terminal. Now write it down. Write it down. This is the magnetic force. So direction is given by right hand thumb rule. Hamza, now take the screenshot of this again. And Nida, note it down. Hamza, taken the screenshot?
1 minute.
Okay, fine. Done. Okay. So Nida, have you
Okay,
changed
done.
this? Yeah, okay, good. Change the polarity. Write this now. Here you have to consider the electron. Okay, fine, good. So now write down this angular, what is angular velocity? This thing will be used now in the next derivation. So direction of your this velocity, and this velocity is also known as the linear velocity, is tangential. Okay. And talking about the direction of the angular velocity means a rotational quantity we have. So the direction of the angular velocity will be along the axis about which the particle is rotating. Okay. So we will do one derivation and I will use this result. Okay. This omega, what is omega? And one more thing I want to add here, the relation between this omega and the linear velocity. So your linear velocity is equal to radius of the circle in which the particle is moving, they multiplied by omega. So note down this result. P is equal to r omega when the particle is moving in a circle. This thing I will use. Okay, fine. Okay, so now we will do one derivation, and derivation is the induced EMF induced EMF across ends of conductor when the conductor is rotating, the conductor is rotating in a plane perpendicular to magnetic field to magnetic field with angular velocity omega, with angular velocity omega. So you have a conductor. This is, suppose this is the conductor, and this conductor is rotating like this. This conductor is rotating like this in a magnetic field, and the plane of the conductor, or the plane of the conductor is perpendicular to the magnetic field. Okay, so I am taking the magnetic field here. I am taking this cross magnetic field, means the inward magnetic field I am taking. The magnetic field is inward, and a conductor is rotating. You have a conductor like this. This is a conductor you have. Okay, and this conductor is rotating in a circle like this. Means this conductor is rotating like this. So what will happen? So the conductor is rotating like this. Means suppose this is the radius, and so this is your conductor now. This is your conductor AB. AB is your conductor having a length L, and this conductor AB is rotating like this in a given magnetic field. In a given magnetic field, L is the length of the conductor. L is the length of the conductor. Now, what will happen? The EMF will be induced in this conductor, because we know that when the conductor will rotate like this, so there will be the change in the flux with respect to this conductor. There will be the change in the flux with respect to this conductor. And if there is a change in the flux, then what will happen? Change in flux will lead to the EMF in the conductor, according to the Faraday law. Okay. So that complete EMF in a conductor AB we want to find. AB is the conductor. This conductor is rotating with an angular velocity given omega. Omega is the angular velocity. Omega is the angular velocity with which this conductor AB is rotating. Okay. Now what we will do, we will first calculate the EMF due to the small element of the conductor, and for getting the total EMF across the ends of the conductor, we will integrate. So suppose here I have taken a very small element dx of the conductor at a distance of x from the center. Okay, B is the center of the circle, you can say, or from this is the length of the conductor. Okay, so from this point, this distance is x, the distance between this point V and this dx. Okay, so at a distance x from this point, you have taken the small element dx of the conductor, small element dx of the conductor. So we'll write here, consider a small element of length dx of length dx d, and this is small x dx at a separation x, at a separation small x from the axis of rotation, from the axis of rotation of conductor. So axis of rotation of conductor means this conductor is rotating about this point. Okay, so this conductor is rotating like this, like this. So this is the axis. From here there will be an axis of rotation about which this conductor is rotating. Okay, having angular velocity omega, angular velocity omega. So omega is the angular velocity of the whole conductor. If you will consider any point of this conductor, that point will have the same angular velocity omega. Okay, same angular velocity omega. So I am supposing that small v is the linear velocity of dx element. Let v be the linear velocity of dx element. So this conductor is rotating like this, means all the points on this conductor will be rotating like this, in this direction, like this. Okay, so there will be some linear velocity of all the points. So linear velocity of this dx is this v. I have supposed v. This linear velocity will be like this. Linear velocity. And what will the angular velocity of this dx length? Omega. Omega will be the angular velocity. Okay. V. So can I write here this v is equal to this v. V is the linear velocity. V is the linear velocity. And what is the relation between the v and omega? V is equal to distance from the axis of rotation, that is r, into omega. So what is the distance of this dx from the axis of rotation? This is the axis of rotation. This distance is the x. So you will write v is equal to x omega. V is equal to x into omega. This is your linear velocity of dx length. Dx is the very small length I have taken of the conductor. Now induced EMF in length dx the formula of the induced EMF is given by minus of v into length of the conductor into v. So length of the conductor is dx. Okay, so this will be the very small EMF de, and this de will be minus v, and for the length I will write dx into the velocity v. Now put v is equal to x omega here. So this de is equal to minus v. This is dx. Instead of this v, I will put x into omega. Okay, so finally a small EMF induced in the length dx will become minus of v omega x into dx. Now for calculating the total EMF, or for calculating the EMF from this end to this end, or you can say the EMF between this end V and end A, okay, will be given by the integration. So we will do the integration. So right here, for induced EMF across ends of conductor we will do the integration on both the sides. dE is equal to, this will be minus V omega x into dx. So integration of dE will become small e, this d will be removed, and here out of the integration we will take the constant term. This magnetic field will be constant, omega is the constant. So we have minus V omega as the constant, and we have x into dx. Now here the integration of x into dx, I have already told you, I think, to Hamza. So Nida, do you know how to integrate this? Or and here you will put the limit also, 0 to L. Okay. What will the answer of this? Nida, can you do this? Yes or no? Okay. I have to tell you the integration first. Both of you. So integration. Integration, sign of integration is this, and integration of dx is equal to x. Integration of, suppose x dx is written, so it means you are doing the integration of this. This is x, not n, this is x. I write x like this. So what you will do, you will write x, increase, this is a power 1 of the x, you will increase 1 power of the x. Here is 1, here you will write x square divided by 2. You will write x square divided by 2, and here you will have some constant c. Okay, now x square dx, x square dx, here is x to the power 2. So when you will integrate it, it will become x cube, and this 3 power will come in the denominator, plus c dash, any constant. Suppose I am saying x, integration of x to the power 4, 4 into dx equal to. So now tell me, Nida, what will be the answer? X to the power 4 dx, I want to write. What will be the answer of this? This is power 4 here. Just do this. Here is power 2, so here is power 3, and this 3 will be in the denominator. Here is power 4, so here it will become x to the power 5, and here will be 5. Yeah, yeah, good, fine, x to the power 5 plus 5 plus c. Okay, so Hamza, now tell me, x to the power 6 into dx, what will be the answer? This is written
X raised to 6 by 6 plus c.
no, this is x to the power 6. Okay, see here, this is x to the power 4. Here you will write 1. Yeah,
X to the power 7 by 6.
7.
By 7.
7,
7.
7 by 7. So this quantity, this number you will write in the denominator. Okay, plus constant will be there. And what we will do, this is the integration, this is the indefinite integration. There are two types of integration. Integration with limits is the definite integration. Integration without limits is the indefinite integration. So in indefinite integration, there is one constant also. Indefinite integration. Now definite integration. Definite integration, the rules for the integration will remain same, but you will just apply the limit. definite integration. So I am taking all the questions from here. Okay. And we will do now the definite integration of all. Okay. So what you will do in the definite integration, first of all, this constant will be removed. This constant will be removed in the definite integration. Here will be some limit. Suppose this limit is from uh, x1 to x2. X1 can be any value, x2 can be any value. So what you will do, you will just write like this. This is x1 to x2. So first you will put the value of x2 in x. So this will become x2. Then you will put the value of x1 in x. This will become x1. So this will be your answer. Suppose this limit is from 0 to x, 0 to x1. So what you will do? You will write the limit of this 0 to x. So first you will put, this is known as the upper limit. This is known as the upper limit. See, this is upper limit. Upper limit. This is lower limit. Lower limit. So here first you will put upper limit in this. So this is x1. So you will get here this 1 by 2 you can take out of this. Okay, this 1 by 2. So you will have this x1 is square minus 0. 0 square means 0. So you will get half of x1 square. Now I am just writing 0 to L is your limit now. So here you will write 0 to L. So you will write this 1 by 3. You will put this L in x cube. So this will become L cube minus 0 cube. Okay. Suppose your limit is from P1 to P2. P1 to P2. So you will write here the limit P1 to P2. So this will become 1 by 5. Now you will put this P2 in this function, in this x to the power 5. So this will become P2 to the power 5 minus P1 to the power 5. Okay. So this is the definite integration now. Here, come here. Okay, now we will solve this. So this is EMF E. So this is minus V into omega. Here is x dx. The integration of x dx from 0 to L you will do. It will become x square by 2. This will be limit from 0 to L. This will become half of L square minus 0 square. Okay. So VL you will write here half of L square minus 0 square. So finally you will get the answer minus V omega L square divided by 2. So this is your final answer. This is your final answer. So this is the EMF induced across the ends of a conductor which is rotating in a given magnetic field which is perpendicular to the plane of the conductor, and the conductor is rotating with an angular velocity of omega. Here B is the magnetic field, omega is the angular velocity with which the conductor is rotating, and L is the length of the conductor. Okay, so this is the formula you should know. And here I have just applied the limit from 0 to L because I want to find this x is varying from, x is changing from 0. At this point the x is 0, and at this point the x is equal to L. That is why I have put the limit 0 to L. Okay, just note it down. So Fawaz.
हाँ सर.
Hmm. We are discussing here the induced EMF. Okay.
Okay sir.
Hmm. So this is the induced EMF when the wire, when a conductor is rotating in a given magnetic field. Okay, this AV is the conductor here. Your AV is a conductor, and this is a conductor having a length small l. Okay, and this conductor is rotating in the magnetic field. Okay, this is the magnet. This is the inward direction of the magnetic field. This cross represent the inward magnetic field. Okay, so this conductor is rotating in the given magnetic field. So you will get the formula of the EMF induced in the conductor AV. EMF induced in the conductor AV is V omega L square by 2. This formula you will get. V is the magnetic field in which the conductor AV is rotating. Omega is the angular velocity with which the conductor is rotating. L is the length of the conductor. Okay.
Okay.
So this EMF you will get when you have a conductor which is rotating in the given magnetic field. Nida and Hamza, both of you please write down. Done. Okay, good. So I have just completed this derivation. For the next topic, uh, you will get what I am teaching.
We're done.
Okay. Remember this formula. I will use this formula in the next numerical. If you don't know the derivation, if you have only remembered the formula, then it's okay. You can solve the numerical easily. Okay, good. So if you want to write down this also, then you can write. So this is the integration, indefinite integration. How to integrate a function. Hamza, take the screenshot of this. Okay. Now complete this. No need to write all the parts. You can write one or two parts. This is just for your understanding. Okay, good. So now I am taking one numerical and I will use this formula. Okay, so numerical. So they are saying a wire of length 2 meter is rotating with an angular velocity with an angular velocity 5 radian per second 5 radian per second in uniform magnetic field in uniform magnetic field of 10 Tesla. Calculate EMF induced across ends of conductor or wire. So here is a wire. Here is a wire, and suppose this is a straight wire, and this wire is start rotating in a magnetic field is around it, and this wire is start rotating like this in a magnetic field. Okay, start rotating with respect to this point. Okay, rotating like this, like this. So what will happen? There will be the induced EMF in this wire. Okay, Fawaz, there will be
Okay, sir.
induced there will be induced EMF in this, and the formula of the induced EMF is this. You will just apply this formula, you will get the answer. E here is the induced EMF. This we have to find. And V here is the magnetic field in this formula. Omega is the angular velocity. Omega is the angular velocity. L is the length of wire or conductor. Length of wire. Okay, right answer. Negative or positive, Nida? Okay, your answer is correct. Okay, right. So E is equal to, just write all the values. See here. Here, see in this question, a wire of length 2 centimeter. Length means small l is the length of the wire. 2 centimeter is given. Not 2 centimeter, 2 meter is given. Okay. So write down here meter. Length of 2 meter is given, rotating with an angular velocity. Angular velocity. This is the angular velocity. 5 radian per second. Angular velocity means omega is given 5 radian per second. And magnetic field, see the magnetic field in a uniform magnetic field. Magnetic field of 10 Tesla. Tesla is the unit of magnetic field. So 10 Tesla is given. We have to find this small e. Small e is given by minus V omega L square by 2. So put all the values. Minus V is given as 10. Omega is given as 5. Length is given as 2 meter. So 2 and square of this. Because in the formula we have length square and divided by 2. So what will the answer? This is 10, 5s are 50, and this is 4. This will become minus 200 by 2. So you will get minus 100. Unit of EMF, SI unit of EMF is volt. Volts. Okay. So Fawaz, got it? This means how to put the values in the formulas.
Yes, sir.
Very simple. Okay. So if you want to note it down, Fawaz, then you can write it. Okay, Hamza,
Yes,
take
sir,
the
I am
screen.
writing.
Yeah.
Yeah, I am writing it, sir. 1 second.
Okay, good. Very good. Written. Okay, good. Fawaz, when completed, you can ask me to scroll down.
Yes, sir. I wrote the answer. It's finished.
Okay, fine. Good. Okay, so now the next topic is the mutual induction. Mutual induction. So see what is mutual induction. So mutual induction, I will explain you with the help of two coils. I will take two current carrying two coils, okay, and I will explain that with the help of those coils. This is one coil, and another. This is the galvanometer we have. This is the galvanometer we have. See what will happen. Here is this is battery. This is battery. This is coil number 1. This is coil number 2. So basically we have this coil, and this coil is connected with battery, and this is the switch. This time this switch is open. This time this switch is opened. Okay. And this second number coil is connected to the galvanometer. Okay. So this time there is no deflection in the galvanometer. Means there is no current in this coil, and right now there is no current in this coil also. So now what I am doing, I am just closing this switch. I am just closing this switch. I have just closed this switch. So what will happen? Here is battery. Due to this battery, EMF of the battery, the current will starts increasing in this circuit. In this circuit, or you can say indirectly, the current will start increasing in the coil. So here will be some current I1. Okay, I1 will be there, and when you will close the switch, this switch you will close, then this current I1 will start increasing. So what happen? This current is in this coil also. Okay, here also the current is I1. So this current, when this current is flowing in this coil and this current is increasing, so we know that due to the current the magnetic field is generated. Due to the current the magnetic field is generated. So due to this current carrying coil, the magnetic field will be generated, that is V1. That is V1. V1 is the magnetic field due to coil 1. Magnetic field. Okay. V1 represent the magnetic field due to the coil 1, and this magnetic field will be directly proportional to the current. We know that if you will increase the current, this magnetic field will be increased. Okay, if you will increase the current, so magnetic field is directly proportional to the current. V is the magnetic field, I is the current. So here when you will close this switch, current will increase, magnetic field will increase, and see this magnetic field will be here also, because these coils are like placed like this. This is one coil, this is another coil. So magnetic field of this coil number 1, will affect this coil number 2. Means you can say this coil number 2 is linked with the magnetic field of coil 1. Okay, coil number 2 is linked with the magnetic field of coil number 2. If you will increase the current in this coil, so magnetic field in the coil 1 will increase. Okay, so you can say that there is a term magnetic flux. Okay, magnetic flux means number of magnetic field line crossing the unit area. So here will be the magnetic flux due to this coil 1, and this coil 2 will be linked to the magnetic flux produced by this coil 1. So as the current will increase, the magnetic field will increase, and magnetic flux is phi. Phi is the magnetic flux. Formula of magnetic flux I am writing. That is, first write what is phi. Phi is magnetic flux. Magnetic flux is given by the magnetic field into area. Okay, into area into cos theta. Theta is the angle between the magnetic field and the area vector. So here you can say that if your cos theta is maximum, so you can remove the cos theta, because cos theta maximum means cos 0, and this cos 0 is equal to 1. So I can remove it. So your flux is basically magnetic field into area. Okay. So as the magnetic field will increase, so the magnetic flux linked with the coil 2 will increase. So suppose phi 2 is the magnetic flux. Phi 2 is the magnetic flux linked with coil number 2. Coil number 2. So the formula for the phi 2 will be, this magnetic field V1. Okay, this magnetic field will be here, na? This magnetic field will be here also. Here the magnetic field is producing. Okay, so V1 into area of this coil A2. A2 is the area of the coil A2. So this will be phi 2. This will be the phi 2. Phi 2 will be the flux, magnetic flux linked with the coil number 2. And what is the cause of the magnetic flux? The current in the coil 1. If you will increase the current, magnetic field in the coil 1 increase. So you can say the magnetic flux linked with the coil 2 will increase. So what will happen? When this flux change in flux with respect to time give you the EMF. Okay. So whenever the flux linked with the coil, here flux linked with the coil will change. So due to the change in the flux, there will be the induced EMF in this coil, and due to the induced EMF, there will be the induced current in this coil. You can write, when key is closed, current in coil 1, current in coil number 1 will increase. Due to current increasing in coil number 1. If the current is increasing in coil number 1, then you can say the magnetic field will be increased due to the coil 1. So you can say magnetic field you can say magnetic field due to coil number 1 will increase. So you can say if the magnetic field in this coil 1 will increase, so this coil 2 is in the magnetic field of coil 1. So you can say the magnetic flux linked with the coil 2 will increase. You can say the magnetic field to the coil 1 will increase. So you can say so magnetic flux linked with coil 2 with coil 2 will increase, and whenever the magnetic field with respect to the coil is changing, either increasing or decreasing, there will be the EMF induced in the coil, and due to that induced EMF there will be the induced current. So magnetic flux linked with the coil 2 will increase, due to which the EMF is induced in coil number 2. So the current means the current will also induced. So what you can analyze from this, if you are increasing the current here, if you are increasing the current here, here will be the induced current in the second coil. Okay. Whenever you are changing the current in this coil number 1, there will be the induced EMF or the induced current in the coil number 2. This is the mutual induction. This is the mutual induction. You can write here, whenever current in one coil change, EMF is induced in the neighboring coil. Neighboring coil. So see here, you are changing the current in this coil, in the neighboring coil, there will be the induced EMF. Simple. And you can say, due to change in current in coil 1, when you will change the coil, when you will change the current in this coil, means either you will increase the current or you are decreasing the current, there will be change in the magnetic flux linked with the coil 2. If you are increasing the current, then the magnetic flux linked with this coil 2, see here, magnetic flux linked with the coil 2 is directly proportional to the magnetic field. So when you will increase the, see here, this is the magnetic flux linked with the coil number 2, phi 2. So this is the magnetic flux linked with the coil 2 is depending upon the magnetic field 1. So when you will increase the current, V1 will increase, this phi 2 will increase. When you will decrease the current, V1 will decrease, phi 2 will decrease. So you can write, due to change in current, due to change in current in coil 1, 1 flux linked with coil 2 will change EMF induced in coil 2. EMF induced in coil 2. So this is the whole story of the mutual induction. Mutual induction is what? Whenever you are increasing the current or decreasing the current or changing the current in coil 1, induced EMF will be, there will be an induced EMF in the coil number second. Okay. This is simply the mutual induction. Just note down this. So here now you can change the deflection of the galvanometer. There will be some induced current here. So there will be some deflection in the galvanometer. Galvanometer is used to detect the current. So here will be some deflection in the galvanometer like this. Because here the current is induced, I. You can add this point also. I is the current induced. Small I. Okay. Fawaz, you are also you are writing now? Should I
No,
scroll
sir.
down?
No, done, sir.
Okay, fine, no problem. If you don't want to write this theory from here to here, you can skip this, okay? If you want.
Sir,
Otherwise,
I
you
wrote it.
can.
I wrote it, sir.
Okay, no problem. Fine. So in from here to here, I have explained what is happening. Okay. So Nida, you have completed this part also. This part from here to here. Okay. Some Hamza, have you taken the screenshots? Okay, now I'm moving. So this is the mutual induction, means due to the one coil, there will be the induced EMF and the induced current. in the another coil. So now, what is the basic thing here? The flux in the coil 2 is directly proportional to the current in the coil 1, because if you are increasing the current in the coil 1, flux in the coil 2 will, flux linked with the coil 2 will increase or decrease accordingly. Okay. So when you will remove this proportionality sign, you see here is 5 to, this is the proportionality sign, this thing. When you will remove this, you will write equal to sign, and here will be some constant m21 and into I1. M suffix 21, this is not m21, this is m suffix 21. M suffix 21. So what is this m suffix 21? This m suffix 21 is the coefficient of mutual induction. Coefficient of mutual induction of coil 2 due to coil 1, due to coil number 1, due to coil 1. And this is the coefficient of mutual induction. Basically, this is constant for some given condition, not always. Okay, this is constant for some given condition. Okay, so now this M21 depends upon certain number of things. Practically, it is found that this coefficient of mutual induction is depending upon the number of things. Number one, it is depending upon the separation between coil. Separation between coil. Separation between coil means if the coils are close, then the coefficient of the mutual induction will be more, and when the coils are far, then the coefficient of mutual induction will be less. Why? Because the mutual induction will reduce when your coil will be the distance will increase in between the coils. Okay, because the flux between the coil or the flux linked with the another coil, okay, so will decrease. Okay, if you will increasing the separation between the coil number 1 and the coil number 2, the flux linked with the coil 2 will decrease because of the magnetic field will decrease. Okay, with respect to the coil 2. So depend upon separation in the coil. Second part, the orientation. Orientation means how you have placed the coil. Means one coil is like this, another coil is like this, and one coil is like this, another coil is like this, one coil is like this, another coil is like this. If you will change the orientation of the coil with respect to each other, then there will be change in the mutual coefficient of mutual induction. So orientation number third, depending upon the geometry of the coil. So geometry means what type of coil you have. Okay, what type of coil you have. Number fourth, nature of the material. Nature of the material of, because these things, I am not saying these things, but this is find it out practically. Okay, experimentally you can say it is find it out that coefficient of mutual induction is depending upon the separation, orientation, geometry, nature of the material of the coil. Material of the coil means the coil is of which type of material the coil is made up of. Okay, so
Sir, can you explain the second one?
this orientation.
Yes, sir.
Okay, orientation means suppose this is your one coil, this is your coil number 1, Okay, and this is your coil number 2. So this time, suppose your coefficient of mutual induction is something, suppose M1. Now if you have just changed the orientation means the direction. This earlier the coil is like this, now the coil is like this. In this time, the coefficient of the mutual induction will change. Okay.
Okay, sir.
Yeah. Geometry and the nature, you know, geometry, shape. Now we can write in journal, we can write this phi flux is equal to coefficient of mutual induction into current. Phi is equal to mi. Now I will use the Faraday law. So for what, see here, what is Faraday law? For Faraday's law. So Faraday says that suppose if you are having a coil, this coil, and you have a magnet here. This is this is the coil and this is the magnet. And this magnet is moving in this direction. Towards the coil, the magnet is moving. So what will happen? Due to this magnet, there will be the magnetic field here across the coil. Is it or not? This magnet will produce the magnetic field. Okay. And now this magnet is moving. This magnet is moving like this. This magnet is moving. Suppose initially the magnet is here and this magnet is moving. If the magnet will move, so the magnetic field will increase with respect to this coil, or you can say the magnetic flux will increase with respect to this coil, or you can say the magnetic flux linked with this coil will change. And Faraday law says that the EMF is induced when there is change in the magnetic flux with respect to the time. So d phi by dt, this is phi. Okay, this is phi. What is phi? Phi is the magnetic flux. Phi is the magnetic flux. So this is the Faraday law. Okay. Change in the flux will produce the EMF, and that EMF is equal to change in the flux divided by change in the time. Okay, this is the differential form I have written. D phi is the change in the flux divided by in what time the flux is changing. So I will use this. E is equal to minus d phi by dt. So this E can be written as dy by dt, and this phi I can take from here m into I. Phi is m into I. So now this coefficient of mutual induction is constant for the certain condition. So I can take this out of the differentiation. So the dy by dt, you will write this E is equal to m di by dt. This, in this form, your EMF can be written. Okay. Now from here, this here is minus sign also. Okay. Here is minus sign also. So if I am only talking about the magnitude, so I will remove this minus sign. Okay. So this will become E is equal to this mod of E is the magnitude of EMF. Electromotive force, EMF. This will be m di by dt. So you can write for m is equal to E into di by dt. So this is the mutual induction. Coefficient of the mutual induction can be written in this form also. Di by dt is change in the current with respect to time. Di by dt is the change in current with time, change in current with time Now I will calculate what is the unit of this M. So for calculate the unit of M, we should know what is M. M is, here is EMF, here is di by dt. So unit of EMF is volts. What is the unit of this current? Di. Di is the current here. So unit of this current is ampere. And unit of this time is second, SI unit. So your formula will become volt ampere second inverse. Volt ampere second inverse, and this is also known as Henry. Henry is a unit of this amp. So if I want to say what is 1 Henry, 1 Henry, 1 Henry means from this formula, when you will put this mod E is equal to 1, means EMF is equal to 1. And when you will put this di by dt also equal to 1, then you will get the mutual induction, that is mod E divided by di by dt is equal to 1 by 1, you will get 1 Henry. So 1 Henry you will get when you have the EMF of 1 volt and change in current with respect to time as 1 per second, 1 ampere per second. Okay, so you can write this: if rate of change of current, rate of change of current of 1 ampere per second or second inverse induced an EMF of 1 volt, an EMF of 1 volt, 1 volt, then mutual induction of coil is 1 Henry. So in short, we can write this Henry as capital H. Henry is a name of scientist. So write down this. So if you want to ask any doubt, then you can ask me. Here I1 is represent the current in the coil number 1. Okay. Why we are using the Faraday law? Because we want this form. We want to write the EMF in this form. Okay, in the form of the mutual induction and changes current with respect to time. Got it?
Okay, sir.
Let's see. Actually, I have not used the Faraday law here because uh, there are many scientists earlier who have already used this thing. They have already done all the things. I am just explaining what they have done. Okay. So, Nida, you have written this? And Fawad, whenever there is a change in the magnetic flux, okay, you can always use the Faraday law, okay?
Okay, sir.
Yeah. If there is a change in the flux, then you can use always. You can write E is equal to minus d phi by dx. Yeah. Faraday law is simple, means if there is a change in the flux with respect to the time, EMF is induced. We can use this like Ohm's law. We can use many times. Hamza, taken the screenshots? Okay. Okay, fine. So write down this. And Hamza and Nida, you can leave the class after writing this, okay? And for what, please stay for 2 or 3 minutes, okay?
Okay.
Yeah. This is one.
Done, sir.
Okay, so both of you, now we will meet in the next class, okay? Fawaz, you stay here for 1 or 2 minutes. Hamza, you can also leave. Okay, walaikum assalam. So Fawaz, means, is your exams over?
No, sir. My pre-boards are starting in November.
Okay,
November
you
and 25.
November and 30? No, what,
No, November
25?
25. Yes.
November 25. Okay, so how many chapters have you completed?
For like I studied or in school.
Means I'm just saying, I'm saying just in school or by yourself if you have completed that.
Sir, by myself, I studied electrostatic potential.
Good, very
Uh,
good. Current electricity.
uh,
Means have
no,
you have,
not.
okay, just I
I
am
will.
asking.
Yeah.
Okay, no problem. So have you completed that electric field, means the electrostatics part, that
Yeah.
electric field, electrostatic potential and all that?
No, sir. I didn't. I just started
Okay,
from 1 week.
you have started from the electrostatics.
Yes, sir.
Earlier you have not done that.
Studying? No, sir. I didn't.
Okay. So resistance and all that, sorry, cell, combination of cells, these things.
Resistance combination. No, sir. I have an idea about that, but
I'm just
I
asking,
think
means you have not completed that, eh?
What, sir?
Okay. I'm saying, have you completed that current electricity chapter? In current electricity,
Notes?
we have.
I
We,
have the notes
Acha, you
in
have.
school. Yeah, I have everything.
And in magnet, what you have completed? Mm,
Uh,
well, no
uh,
problem.
yeah, yes, sir. Yeah.
So I'm saying that no problem if you have not completed. Uh, so here in this batch, actually, this chapter is going to finish in one lecture. This is the chapter electromagnetic induction. Have you heard the name electromagnetic induction?
Yes, sir. Yes, sir.
Okay. Uh, so magnetic induction will be finished in the next lecture, and here I will start the alternating current. Have you heard the name alternating current?
That's chapter 7, right?
Yeah, yeah.
Yes, sir.
Alternating current. So I will suggest you to just join the classes and start with the alternating current right now for the situation you have. Okay. And what we will do accordingly, you should revise your notes, that previous notes you have.
Okay, yes, sir.
You have the
Yes,
notes now of electrostatics and
yes, sir. I
magnetism.
have. School notes, I have everything.
Yeah. Because if we will start from the electrostatics, then uh, there are the that will take a certain amount of time. Okay.
Okay, sir.
But the situation is now here. You should join this batch, and I will start from the alternating current. But
Oh,
alternating current, just a minute. From this alternating current chapter to the chapter that I will do after that, after the alternating current, I will start electromagnetic waves, then the optics, and then the modern physics, then the semiconductor devices. All these things
okay.
we will do. So first, now you should start from this. In the backup, you have the electrostatics, current, electricity, and magnet. These three chapters you have in the backup. You should revise your notes. Okay. And we can do that in the extra class. Okay. If you want to complete that, we can do in the extra class.
Electrostatic, I will finish it by myself.
Very good, well done.
Yeah, yes, sir. I can
So
do it.
now, if the electrostatics is a means, I will see the big part of the electromagnetism. Electromagnetism means the electrostatics, current, electricity, and the magnet part. Okay, this is the electromagnetism, and the EMI is also the part of electromagnetism. So
Okay.
if you have completed the electrostatics, means current electricity is 50% easier than the
Sir,
electrostatic.
but current electricity is a big chapter. I am confused of that. Can
Okay,
you?
so what we will do now, we will take the extra classes. Okay.
Okay.
And in the extra classes, if you will have doubt, then we will try to solve your doubt also. And
Okay.
if there will be problem in some topic, then separately we will study those topics. Okay.
Okay. But
So
extra classes will be after this alternating current and all this, or
yeah,
it will be.
no, extra classes will be after this, because in this too, so we will study alternating current. Okay.
Yes, sir. It will be
Because
confusing if
uh,
both chapters is,
hmm?
both chapters. If we go at the same time, then I will be confused. But
I know that. So you can choose the alternating current. You can just
ah,
study the alternating current, no problem. But I am just saying that you are saying your examinations are coming. So at least if you don't want to that, you don't want to study both with me, then at least try to just understand those chapters by yourself. Try. Okay. If what you will
okay.
do, if what you will do in your exam, then you
Sir,
should.
it's okay. It's pre-board. I will manage. But
Okay.
for finals, I want to be ready for it.
Yeah, because you are right,
Yeah,
you are right,
yeah. Thank you.
because this is the pre-board. If
Yeah.
in pre-board, what is the just significance of the pre-board, I am telling.
Yes,
In
sir. It's
pre-board
preparation.
examination, they check the student, means where the student will do the mistakes for the
Yes, sir.
and that will be better for the final examination. If you do the mistakes, you can do here. Okay, not in the final exam.
Yes,
So
sir. Yes.
just I am saying that just try little from this time, try some part of the electrostatics to revise. Okay, when you will do the revise small chapters, small part, till when will your final examination?
Final, I guess February. In February.
In Feb, na? So till Feb,
Yes,
your all the chapters will be completing smoothly. Okay,
yes,
so
yeah.
your target should be like this. Your target should be the final exam. So
Yes, sir.
somehow you have to perform well in the final exam. Okay,
Okay, sir.
and